Okay, I would like to present you some results of my PhD work about improving the measurements of nitrogen dioxide with Mark IV brewers. Maybe there will be some overlap with the previous presentation I gave to the training school, but then I will go into details. Okay, so you already know that Mark IV and Mark III brewers are able to measure nitrogen dioxide in the atmosphere. Mark Brewer was developed exactly to this aim, being able to measure in the visible range. The original algorithm was developed in the last 80s by Kerr, and it is the one employed in the current software, in the Brewer operating software. Some updates were done by David Barton in Environment Canada, and they are not implemented in the current software. So the software still works with the old algorithm. And it has some problems because some great overestimation were found during campaign compared to both other ground-based measurement and satellite radiometers. You will also probably notice in your data some random deviation, probably due to interferences or the sensitivity to instrumental settings, especially wavelength misalignment, slight wavelength misalignments. Some algorithms are very noisy to retrieve this gas. This is a very weak absorber, so it's not simple, it's not straightforward to retrieve it. And finally, no calibration service is performed during the on-site calibration. But in addition to these problems, there are many open questions. For example, can we move the grating position, the standard weighted position, and choose a different set of wavelengths, which is more effective, which is optimal for the retrieval? And how large is the measurement of certainty in nitrogen dioxide measurement? I think this is also a question for ozone measurements. And no published paper exists on the comparison between the results using direct sun measurement and zenith sky measurements for nitrogen dioxide. Also, the Langley plot is not straightforward because Langley's plot is usually strictly defined for Sable absorbers during the day, while the nitrogen dioxide increases during the day due to the photochemistry. So this is a problem. And finally, it is possible to apply any new algorithm to all series. There are very long series back to the 90s, for example, and they would be very useful information for the network. What I tried to do during my PhD work was to develop a framework based on mathematical framework based on the characterization of the brewer and the parameterization of every influencing factor on the retrieval. I completely updated the spectroscopic dataset, that is the cross sections. I calculated new air mass factors for the zenith sky geometries. They must be polarized because photons coming from different polarization follow different paths in the atmosphere. So you have to calculate two different air mass functions for every polarization. I tried to overcome the problem of the Langley plot, then we see how. I used the Monte Carlo technique to calculate the uncertainty budget, and then I applied the new algorithm on 4 European series. I skipped the instrumental characterization since I already had a presentation in the last Brewer meeting in Beijing about that. I just tell that this is a very important task because of the weak power of the nitrogen dioxide to absorb the radiation in this range, and the the low concentration of this gas. For example, for ozone we have about 300 Dobson. For the nitrogen dioxide, the stratospheric conditions are 0.1 Dobson. So you must be very careful with your characterization in order to distinguish between the instrumental effects and the real natural signal. Okay, the updates of the algorithm. The new algorithm uses all the 6 slits in the visible range. 4 degrees of freedom are used to cancel out the effect by the Rayleigh scattering, the ozone absorption, the aerosol extinction, and a constant term. So you end up with 2 remaining degrees of freedom. One is used, as in the standard ozone retrieval, to normalize the weightings, but you have another that you can use to rotate the weightings and choose a new set of weightings in order to reduce noise and to increase the signal-to-noise ratio. And you obtain this by aligning the weighting vectors to the cross-section vector. It is a linear algebra formulation, but it is quite nice. Then I considered every factor that could degrade the nitrogen dioxide retrieval, and I established its influence for every grating position and every set of wavelengths that can be used in a Mark IV brewer. That's because I wanted to find an optimal position of the grating that increase the sensitivity of nitrogen dioxide and decrease everything else. The considered factors are noise, the influence by the oxygen dimmer. You see there is a slight influence of the dimmer, it's the green one here. Water vapor, the ring effect in the zenith sky measurements, the sensitivity to the effective temperature of nitrogen dioxide, and also slight wavelength misalignments remaining from the HG test. And then I found 3 different optimal positions that increase the signal-to-noise ratio for nitrogen dioxide and decrease almost everything else. 2 of these steps are very close to the standard position, and the remaining is quite far. This would be an interesting point, but there the sensitivity of the brewer is very steep, so we have dead time problems, as we told before. A completely different technique I also employed uses 11 slits, 11 wavelengths. You can swing the grating into different positions, like in, for example, in Unker measurements, while keeping fixed one wavelength for cloud screening purposes. So you have 11 independent pieces of information that you can use, for example, to include the oxygen dimmer and the water vapor inside the retrieval of the nitrogen dioxide. Further updates concern the cross-section, as I said before. I updated them following the last NDAC guidelines. You can see the difference between the dates of the old cross-sections using the standard algorithm, 76, 52, to the new ones. Also, the I0 effect is taken into account. I added a bit of nitrogen dioxide when convoluting the cross-sections in order to take into account the Fraunhofer structure of the solar spectrum. A new set of weighting factors were calculated, and then I calculated the polarized air mass factor for the zenith sky geometries using Shiatran, which is a full spherical and vector model. Okay, this is an interesting graph because it represents a retrieval on a synthetic spectrum from the Libratran model. I put here in the example 1 Dobson unit into the model, and then I tried to apply my algorithm to the model, and it agrees quite well. It is represented by red crosses. While the old algorithm greatly overestimates the input value of nitrogen dioxide. This difference is due to the filter correction. If you don't take into account the non-neutrality of your neutral density filter, you have this error. And the remaining is due to the old set of cross-sections that are used within the algorithm. Then I organized an ad hoc campaign to validate the method and to calibrate my brewer. You should recognize this place. It is Isania, of course. Here, the problem is the Langley plot, as I said before, because you have a variable absorber. And in the literature, this issue was solved by using really complex photochemical models and modifying the air mass factors according to the photochemistry. I prefer to adopt a much simpler approach based on the fact that the daily increase of the nitrogen dioxide is linear with time within about 80 degrees of solar zenith angle. So you can add a linear term in the Langley. You can, let's say, generalize the Langley plot by inserting this linear term with time. And an inversion matrix, a matrix inversion gives you, at the same time, the extraterrestrial constant, the vertical content of the nitrogen dioxide in a day, and the daily variation. And fortunately, this daily variation is quite compatible with the previously reported results in the literature. Okay, these are all the results of the campaign for the 3 different geometries as a function of the air mass. You see that they are almost the same within their uncertainty. With the direct sun measurements and the zenith measurements in the parallel polarization quite perfectly overlap, while the perpendicular polarization is a bit higher. And that's probably due to remaining ring effect. And in Isania, there is an NDAC reference instrument to measure nitrogen dioxide at the zenith during twilight hours. And this is a scatter plot with the Brewer. You see 2 groups of points, one for the morning and one for the afternoon. And the difference is not so bad, and maybe it can be improved. The scatter also is quite large, but that's because I used a very fast routine for NO2 measurements because I wanted to have many points during a Langley. So I decreased the number of samples from 100, that is the default value for DS measurements, to 16. So the noise also can be improved. Okay, skip this one. This is the graph resulting from the Monte Carlo uncertainty budget. I took into account all these factors in both the calibration and measurement phase. And you see that the most prominent factors are the Poisson noise that can be reduced, as I said before, and the wavelength uncertainty. So this is quite a problem. This is linked to the fact that the Brewer measures at only 6 slits, and you cannot perfectly derive the wavelength shift from these 6 wavelengths. And we will see some consequences after. This is a comparison between David Barton's algorithm and mine. Mine is in the blue color, and his is in red. And you see that mine is much less noisier than his. That's interesting because this is the very same data sets of measurement at the same wavelengths, and just the weightings change. And if you zoom in one day, for example, you will see that his algorithm is very sensitive to the mercury lamp test results, to slight misalignments of the wavelengths. Here I put on the graph the results from the HG test in the same scale as the nitrogen dioxide scale, and you see that the algorithm follows the changes, while the new algorithm is quite stable with respect to it, because it was optimized to be less sensitive to the wavelength misalignments. Okay, you can play with the data. For example, since you have measurements at 2 different polarization, you can also derive additional products as the degree of linear polarization of the sky. And you see the difference between a clear sky, which is quite polarized at the zenith, and a foggy sky, which isn't polarized. The blue line is the model, which fits quite well, but there is some difference, which I think is not attributed to the model parameters that I tried to change, but to the efficiency of the polarizing filters inside the brewer. 95% efficiency is enough to trigger this difference on the data, from the model to the data. Another additional product, another new product is the oxygen dimmer optical depth, which has some application to the aerosol studies and cloud screening purposes. And you see, for example, the difference between 3 cloudy skies and 2 clear sky days. So the Mark IV brewer is a very powerful instrument, which is probably underused normally, but you can derive many parameters. And then the Brewer 66 calibration was successfully transferred to another instrument, proving that it is possible to calibrate other brewers. Finally, I tried to apply the algorithm to other European series, to 4 European series. Here the problem is that we don't have the calibration, and I couldn't move my brewer in all those different places. So I used some statistical techniques as the minimum amount Langley extrapolation or the bootstrap estimation that are described in more detail in the paper by Herman. But when I first applied the new algorithm, I got really disappointed, because in every series, especially the Athens series, there were those gaps, those sudden changes, which I really didn't understand the reason. And after careful investigation, I noticed that all these events are related with the wavelength setting of the brewer. So each time you change the operational step, for example, as a consequence of a SunScan test, or every time you change the HG lamp or you touch the micrometer, you can have these changes. And this fits perfectly with model sensitivity studies. You see a change of 2 steps in the brewer, in the grating position, could trigger a very high change, which is dependent also on the air mass. So you can correct the series, taking this effect into account, and you get a better series. And you can also sort these 4 series depending on the degree of pollution of the site. And it is quite reasonable, since St. Christophe, Aosta is a quite unpolluted site, while Athens is a very polluted site. You also see the overestimation by the old algorithm that are very, very large, very huge. And even in unpolluted site, you can find a correlation between the nitrogen dioxide vertical column, which is the whole atmosphere, troposphere and stratosphere, and the results, the measurements by in situ stations, which only proves the lower layers of the troposphere. But it is quite interesting that even in Aosta, which is a relatively rural site, there is such a remarkable correlation to the tropospheric content of nitrogen dioxide. You can also see the seasonal cycle with maximum values in winter time and minimum in summer. This has several reasons, both photochemical, dynamicals, etc. You can see the difference between the weekends and weekdays because of the man contribution to the pollution. So Saturdays and these Sundays and Saturdays are lower than the other days of the week. And on an even shorter scale, you can find the daily cycle of the measurements, of the vertical content. You see, these are the morning rush hours when people go working. And this distribution is very different on weekend days, so it's really linked to the main activity. And now I try to compare the brewer ground-based measurements to satellites, and I'm very happy because the brewer measurements have decreased, and the overall bias between among all 4 stations is just 2.4%. But there are still some issues. For example, the seasonality of the brewers is quite low compared to the satellites. I expected the opposite, for example. Future research concerns the aerosol optical depth retrieval at these wavelengths, which is also retrieved by CML photometers, and a more accurate brewer and satellite comparison. These 2 activities will be done during a short-term scientific mission in the UBrewNet framework. Then the ring effect is still an issue for zenith sky measurements, so it deserves a more detailed study. But current models don't support at the same time the rotational Raman scattering and vector and polarized simulations. So this may be a problem. Stratosphere and troposphere partitioning using at the same nearly simultaneous direct sun and zenith sky measurements. And of course, moon measurements in the visible could be a nice try, and it would be quite interesting to see the evolution of the nitrogen dioxide without the photochemistry. Thank you.
I think that's an extremely nice piece of work, and the results are, very useful and very nice. One of the things I was going to ask you is, in doing the Langley analysis, did you look at all about using the period when it's changing very rapidly in the evening and the morning?
No.
This
I
is
discarded it.
That's what we used to do, because the assumption there was that the NO2 would not be changing very fast. It does change, but only by 10% or something. And so an average of a morning and an evening should give a reasonably good estimate of a Langley, right?
Okay.
You'd have to verify that with your model calculations.
Yes.
It's something you might want to consider, because it's a number that probably will be less uncertain because it's lower
Of the air mass. Alexander.
Yeah, I also think it's a very good work that you did. I have 2 comments. One about the polarization. It was surprising to me how good you can retrieve the degree of polarization. I have measured the polarizers in our brewer, and they have between 95 and 90% efficiency.
That's why.
So when you send unpolarized light through, the light that comes out is not fully polarized.
Yeah,
exactly what you said.
There is some stray light from the perpendicular polarization to the parallel polarization.
Yeah.
And I think this can be an issue also for ozone measurement in the zenith sky. So this effect is, I think it's worth being studied in detail.
And my other comment is, I'm not totally sure why it wouldn't be possible also to use the wavelength shift, include the wavelength shift somehow in a derivative in every single scan.
Okay.
Because you have only 6 wavelengths that are 3 nanometers apart, but at least from a theoretical point of view, you could say what would happen if they are a little bit more to the right, a little bit more to the left, and include this. I don't know if you run out of degrees of freedom, but since it seems to be right now that the wavelength shift is the biggest issue.
The biggest contribution to the
Right.
uncertainty.
I think it should be possible to also shift it in the algorithm.